Now we are dealing with actual voltage waveforms, we can revisit our definition of contamination and propagation delays. Remember that the contamination delay of a logic gate is a promise or guarantee that if the logic gate is in equilibrium and then the input suddenly changes, the output will not change for at least the period given by the contamination delay. How do we precisely define, though, the input changing and the output changing? Well, that's determined by whether or not they've crossed these two lines here. This line here for the output, this line here for the input, or if it's high, these two lines. For example, we have a logic gate here. Its input looks like this yellow function here as a function of time. So it starts off at 0, it wiggles, 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 but gradually reaches 5 volts up here. The contamination delay is taken from when the input first changes. But although the input voltage waveform is certainly changing here, it might always be changing due to noise, etc. So we're not actually going to count this as the input changing. Rather, we know that the input is treated as being valid whenever it is below V input low, or if it were high, above V input high. In this case, the input is low, so provided the input is lower than V input low, it's still a valid input. So rather than say the contamination delay starts when the input changes, we should really say the contamination delay stopwatch timer starts as soon as the input A becomes invalid. So while the input's still valid, the input is just a logic 0 and everything is fine. Only once the input crosses the red line here do we consider that the input has started to change, in that it has become invalid, and thus we start the contamination delay stopwatch. When the contamination delay stopwatch expires, we know that the output might start to change after that. And we'll look again at what we mean by change. Technically, it means the output might go from being valid to invalid. Let's assume the output of my logic gate looks like this wiggly curve down here. When do we consider the output as having first changed when speaking about the contamination delay? Well, that's when the output first becomes invalid. And the output is invalid when it's between these two regions here. If it's lower than V output high, it's invalid. And if it's above V output low, it's invalid. Within this region here, it'll be invalid. So therefore, we draw on our diagram V output high, and this is the point at which the output has become invalid. So the propagation delay, and I haven't drawn these to scale, nor have I got the correct output for the given input, but the contamination delay is a guarantee that if we start our timer here and stop our timer here, then that difference in time is going to be at least as great as the contamination delay. In summary, the contamination delay is a guarantee that from when the input first becomes invalid, we have this much time until the output first becomes invalid. To understand propagation delay, let's consider another logic gate, possibly the same inverter. Here's its input signal, here's its output signal. We have time along the horizontal axis. The propagation delay is the time from when the input is valid and remains valid until the output is valid and remains valid. So in this diagram here, the input changes from a logic 0 to a logic 1, but it drops out of the logic 1 state and only re-enters the logic 1 state and remains in the logic 1 state here. In this example, the propagation delay must be less than the time from here. This is when the input becomes valid and stays valid. And this time here is when the output becomes valid and stays valid. So however long it took from this point to this point must be less than the propagation delay, because the propagation delay is a promise that as soon as the input has become valid and remains valid, that the output will become valid and remain valid within the propagation delay amount of time.